Right. So how many of you have used ion pair chromatography so far or ion pairing reagent so far? Type in yes or type in no in the comment box. It doesn't matter in case if you're not yet used that. We are going to talk about the ion pair chromatography for sure, but just to understand the audience. Awesome. Thank you so much that many of you have used this chromatography and some of you are not yet used. Don't worry. We will try to understand from its very fundamental level. So this is your stationary phase, like a non-reverse phase chromatography. See, if I ask you, what is the biggest challenge in the reverse phase liquid chromatography? What will that be? What is the biggest challenge in the reverse phase liquid chromatography? Hmm? Jay Kumar, no worries. What is the biggest challenge in the reverse phase liquid chromatography? Please type it. Retaining the polar compounds. Mina, you are absolutely right. Retaining the polar compound or ionic substances. Yeah, absolutely, Mahabjin. Thank you so much. Poor retention time for. So how one can retain these polar compounds for longer time again onto the reverse phase liquid chromatography? Come on. How one can retain these polar compounds for longer time even though by using the reverse phase columns? What is the nature of the reverse phase column? Is it hydrophilic or hydrophobic? Hmm? Absolutely. Is it hydrophobic, isn't it? It is the non-polar. So what is the law attracts like rule says? If you have the normal hydrophobic stationary phase, you are going to have the good amount of interaction for the hydrophobic or non-polar compound. But you will not have the good amount of interaction for the polar or hydrophilic compounds. So what is the simple hack? Can you convert your so-called reverse phase liquid stationary phase a little polar? And that is the reason we are talking about the ion pair reagent. That's the reason we're talking about the ion pair. So you are going to add some polar, the sites onto your stationary phase. You are going to add some polar sites onto your stationary phase. And what are those sites? Actually, they are called as the ion pairing reagent. They are called as the ion pairing reagent, and they have to be added inside the mobile phase or the mobile phase. And once the mobile phase travel onto the column, this so-called ion pair reagents gets connected with this hydrophobic stationary phase and make your stationary phase a little polar. But let us now understand how this actually takes place. So this is the stationary phase you have at the beginning. And this is the nature of the your ion pairing reagent. So this is the what is the nature of the ion pairing reagent? What is the example I am talking about? What is the name of this ion pairing reagent? Hmm? Yeah, come on, what is the name of this reagent? I'm sure most of you might have used this ion pairing reagent. What is that? What is that? Is it network Vishu? Sulfonic acid, only sulfonic acid? Is it N-hexane? N-hexane. It is not octane, but it is N-hexane sulfonic acid. Sodium salt of N. How many of you have used this reagent? Type in me in the comment box. And this is nothing but the ion pairing reagent. This is one example of an ion pairing reagent. So understand the structure of the ion pairing agent now. See, what is the nature of our stationary phase? What is the nature of our stationary phase? Our stationary phase is non-polar or hydrophobic in the nature. Yes or no? Our stationary phase is hydrophobic in the nature. And if you go with the like attracts like rule, if you go with the like attracts like rule, the hydrophobic nature of the stationary phase can attract the hydrophobic part of our compound. Hydrophobic part of our compound. So what is the hydrophobic part of this ion pairing reagent? Is the carbon chain hydrophobic or sulfonyl end is the hydrophobic? That is, alkyl chain is the hydrophobic in the nature. Alkyl chain is the hydrophobic in the nature. SO3 minus is purely hydrophilic or polar in the nature. Now, what is the effect? Once this alkyl chain gets bonded onto the stationary phase. Now, what is the active site available onto the column then? What is going to be the active site available onto the column? SO3 minus, isn't it? That is the polar part of this ion pairing reagent will be available for interaction of with our analyte. So now let us understand. It's a very interesting phenomenon to understand. So this is our so-called hydrophobic stationary phase. And you understand the ion pairing region. Now this brown colored region is what? Is it a hydrophobic or hydrophilic end? Understand this point, right? So this end is the hydrophobic end, right? Hydrophobic end. Now the moment this ion pair reagent is added inside the mobile phase, where this reagent is added into the mobile phase, and this is the column connected, example C8, right? So why this is the situation? Why this end is going to get connected onto the C8? What is the reason for that? You understand this point? Why not this Na plus is connected onto the C8? Why this another end of the Na plus is connected with the C8? Non-polar, non-polar, isn't it? Hydrophobic, hydrophobic interaction, like attracts like, right? Type in LAL for like attracts like in the comment box. Because our hydrophobic end of this ion pair reagent is going to get connected with the hydrophobic property of the column or the stationary phase. And that's how our Na plus or the polar end is available on the another side. Are you clear on this point? Type in C for clear in the comment box. Why this is the arrangement possible on the stationary phase if you add the ion pairing reagent. Clear? Type in C. Now, what is the important point to understand? We call that our stationary phase has become little polar now. You agree with me that the stationary phase has become polar now? So-called C8 is not available for the interaction, but now the SO3 minus end is available for the interaction, and SO3 minus is highly polar functional group, yes or no? So can we now say that our stationary phase has become polar? Yes or no? Is it polar or non-polar? After having the in situ addition of this ion pairing reagent, the nature of our stationary phase has become what? Polar, non-polar. Come on quickly. P for polar, NP for. So it is polar. Now, if the stationary phase is polar, what should be our compound? Our compound should also be polar, yes or no? Otherwise, if our compound is non-polar, can there will be interaction? If our compound is non-polar, will there be interaction, yes or no? Absolutely no interaction, or very less poor interaction. The first important point is we need to make our compound polarized. We need to make our compound polar. And how the compound can be made polar? By ionizing. By ionizing, the compound becomes more polar. So the base can be protonated to BH plus, and that is called as the more polar form of the just base. I'm going to understand this. B to BH plus, which one is polar? B is polar or BH plus is polar? B has protonated to BH plus. B stands for basic compound, and that has protonated to BH plus. Addition of the proton makes the compound more polar. So which compound will have the base interaction? B or BH plus? Please type in the comment box. Which compound can have the more interaction? B or BH plus? Understand this point? Clear? So you have to make sure that our compound is always polarized. Otherwise, there is no use of addition of ion pairing reagent. There is no use of addition of ion pairing reagent. Now this BH plus can compete with Na plus, yes or no? And this BH plus can replace Na plus, and this BH plus can get connected onto the stationary phase. Amazing. Type in A for amazing in the comment box. And now our BH plus, so-called protonated base, our polar compound has got retained onto the stationary phase. You understand this phenomenon? This is called as the ion pairing reagent. This is called as what? Ion pairing reagent. Now this is the basic compound. Now what is the ion pairing reagent required for acidic compound? What should be the charge present onto the ion pairing reagent? Plus or minus? Yeah. Tetrabutyl ammonium bromide, isn't it? It should be a positive charge, not the negative charge, right? The charge onto the ion pairing reagent should be positive or negative to retain the acidic compound, plus or minus. Type in plus in the comment box, isn't it? Plus, like tertiary amine, isn't it? Or quaternary amine, not tertiary, but the quaternary amine, N plus. And your acid should be having which charge now? The ionized acid will carry which charge? Positive, negative charge. Yeah, it is going to carry negative charge. So understand this also, the opposite charges attracts one another, and that's how to retain our negatively charged acidic compound, your ion pair reagent should have the positive charge. Clear to everyone? Type in C for clear in the comment box. Do you understand how the ion pairing reagent works and how the retention takes place? Got the clarity, yes or no?